Right, now we've talked about using row operations to reduce systems of equations to reduced row echelon form. Now we're going to talk about classifying the different types of systems by the types of solutions that are encountered. Okay, so we'll classify these solutions. Some systems of equations, for instance, have no solution. Some have infinitely many solutions. Some have a single solution. We're going to prove theorems that show when these things take place and be able to characterize a little bit better the possible situations that arise. Okay, so let's first start with this definition. A system of linear equations is called consistent if it has at least one solution. Otherwise, the system is called inconsistent. Now, so we're dividing into two possibilities. The system is either consistent or inconsistent. Okay. It will turn out that when the solution set is, when the system is consistent, we'll want to subdivide further. If the system is inconsistent, there's no solution to the system. There's really nothing more to be said. That's about as far as you need to go. Now we're going to characterize the systems in terms of these sets of column indices D and F. Now remember, D was the set of pivot columns and F was the set of non-pivot columns. Remember that a pivot column is one where you have a boxed number, you have a leading one, and all the other entries are 0. So in this case, D would be 1, 3, 5, 8, and F would be 2, 5, 6. Did I count that wrong? Let's start again. 1, 3, 4, 7. 1, 3, 4, 7 would be D, and F would be 2, 5, 6, 8, 9. Okay. So these are going to be important in the characterization of the solution. And you also have R. R is the number of 0 rows. Here R is equal to 1. I'm sorry, R is the number of non-zero rows. Take that back. R is the number of non-zero rows. Here we have 1, 2, 3, 4 non-zero rows. So we have this set of solutions here. Okay. Notice that D and F are disjoint, and together they make up all of the columns. So we call this a partition of the set of column indices. All right. All the numbers from 1 to 9 are included in either D or F, and there's no overlap between D and F. Now, notice that R, which is the number of non-zero rows, is also equal to the number of elements in set D. Why is that? Because in every row, there is a pivot entry. And each pivot entry represents one pivot column, and it also represents one non-zero row. So the number of non-zero rows is equal to the number of pivot columns. So you can see that the number of elements in the set D is always equal to R. All right, so let's look at some examples. This is arch type I with lots and lots of variables. Now we know that we want to start out by simplifying. We want to change this into a matrix form, and you can see what size matrix you're going to have. In fact, you have 4 equations, so the matrix will have 4 rows, and there are 7 variables plus a constant term, so there's going to be 8 columns in the matrix. Now if you take this and do row reduction, and it's a good exercise to do that, you end up with the following form. All right, you can see this also has 4 rows and 8 columns. And from this we can extract the pivot columns. We can also extract the free variable columns, and we can find R. There's 3 non-zero rows, so R is 3. Here we have 1, 3, and 4 are the pivot columns, and all the rest are non-pivot columns. Now, each one of the pivot columns corresponds to a variable. Here we have D1, D2, D3. It corresponds to X1, X3, and X4. And the procedure we're going to use is we're going to solve for these 3 variables, X1, X3, and X4, in terms of the other variables. Now, what are the other variables? Those are the variables that have these indices, X2, X5, X6, X7, and X8. So we can take the rows of this matrix, and with each row we can create an equation, and we can create an equation for the variable corresponding to the pivot entry. For instance, this first one is x1 plus 4x2 plus 0x3 plus 0x4 plus 2x5 plus 1x6 minus 3x7 plus 4 is equal to 4. Sorry, that's the augmented column there. Okay, and we can take that equation and solve for x1, which is exactly what's happened here. Okay. Similarly, with this second row here, this is an equation that we can solve for x3. We can say x3 is equal to 2 minus x5 plus 3x6 minus 5x7. Okay, and that's the equation here. Now, why did I get the minuses? Because I was mentally taking these variables over to the other side where these numbers become negative. Same for the third one. You can work this out yourself. So these three equations correspond to these three rows. I have the pivot variables expressed in terms of what we call the free variables, the variables whose indices are in the set F. Now, the free variables are just that. They're free. There's nothing that determines their values. So I can treat these free variables as free parameters. I could put any value in for x2, any value for x5, any value for x6, any value for x6, any value for x8, any combination of values for these 5 variables, and I can still get a solution to the system simply by finding x1 that satisfies this equation, x3 that satisfies this equation, x4 that satisfies this equation. What this corresponds to is the following solution set. You can see that the values, we let x2, x5, x6, x7 be any values we want. This gives me the value of x1 by the equation up here. This first equation here gives me this result for x1. This equation here gives me this value for x3 down here. This equation here gives me this value for x4 here. I have x1, x3, x4 are determined in terms of the free variables x2, x5, x6, x7. x2, x5, x6, x7 can be anything you want. So this is the general expression for the arbitrary, for all possible solutions to the system. Okay. And here in the book, you're invited to do the same thing with a different arch type, which has similar complication, but you should be able to follow through the discussion and apply the same principles to get the pivot variables in terms of the free variables. Okay. Now here we're using a different notation. Here we talk about independent and dependent variables. The dependent variables are the same as the pivot variables. They're the variables corresponding to the pivot columns. The independent variables are the same as the free variables. Okay, just a different way of saying it. This is a very descriptive way of describing these variables because the dependent variables, that is the pivot variables, depend on the free variables. That's what we saw up here. The free variables could be anything. The dependent variables or pivot variables, the values were specified by the values of the free variables. Okay. So here we have another example with free and dependent variables. Here's a system of 1, 2, 3, 4, 5 equations in 5 unknowns, and you have the constant column. So you're going to have 5 rows, 6 columns. The row reduction of this turns out to be here. Here we have 1, 2, 3 pivot columns. These are the dependent variables, x1, x3, x4. The independent variables, x2, x5. I'm sorry, x2 and x5. This is not a variable. Okay. So notice that F has 2, 5, and 6, but this column 6 doesn't correspond to a variable. Okay, now so this column 6 does not correspond to a variable. There's an important point that's going to be proved later. Notice that this last column, the column 6, which corresponds to the constants in the equations, is not a pivot column. It turns out that if the last column is a pivot column, then the system is inconsistent. Okay. Now, from this form, we can read off, similarly, a form of the solution. Look at this first equation here. This first equation gives me x1 equals, constant is 6. And here this, let's work backwards. This is 1, 2, this is x5, so that's going to be minus 3x5. And then here I'm going to have plus x2. The second one is going to be x3 equals 1. And then here we're going to have plus 2x5. And then here we're going to have x4 equals 9 minus 4x5. So these are the three equations I can pull off. From that, those three equations are duplicated right here. From that, I can find expressions for the dependent variables x1, x3, and x4. And the independent variables x2 and x5 are left free. Okay. All right, now here's the theorem that we were just referring to, that the consistency of a system is determined by this one fact, that if the last column of the reduced row echelon form is a pivot column, if the last column of the reduced row echelon form is a pivot column, then the system of equations is inconsistent, and there's no solution. And this is if and only if. If and only if. So if the last column of the reduced row echelon form is not a pivot column, then you can find a solution. Now, because you're proving an if and only if, you actually have to prove two different statements. You have to show that if column n plus 1 of B is a pivot column, then the system of equations is inconsistent. You also have to show that if the system of equations is inconsistent, then the final column of the reduced row echelon form is a pivot column. Now, the first one of these is easier to prove. So let's suppose that the last column, column n plus 1 of B, is a pivot column. Okay? You can read through these words, but the idea is, let's just take one example. Suppose we have 1, 0, 0, 5, and then we had 0, 0, 0, 1. Here, remember, this is our last column here, so this corresponds to the constants. What equation does this last row correspond to? Well, we have variables x1, x2, x3. They all have 0 coefficients. What this last row corresponds to is the equation 0 equals 1, which cannot happen. Okay? And that's what we're saying here. Whenever you have a reduced row echelon form where the last column is a pivot column, you're always going to get this equation 0 equals 1, which cannot ever be satisfied. So what that means is if the last column is a pivot column, you always end up with a system that cannot be satisfied. Okay? Okay, so as I said, you have to show two things. Let's attack the second thing. For the second half of the proof, we need to show that if we assume the system is inconsistent, then the last column is a pivot column. So we're going to show that inconsistent implies the last column is a pivot column. Now, instead of proving this directly, we're going to use a very common alternative, which is the contrapositive. So this is an important technique. You can read about this in the section talking about it. Instead of showing A implies B, you show that not B implies not A. You can think of various examples that illustrate this. For instance, I can say that I'm in Killeen, therefore I'm in Texas. That's a true statement. That's an A implies B statement. If I'm in Killeen, then I'm in Texas. That's equivalent to the statement, if I'm not in Texas, then I'm not in Killeen. Okay, those two are logically equivalent. You can take you can take many examples of this. Another example, if Fluffy is a cat, then Fluffy is cute. All right, then you can say, if Fluffy is not cute, then Fluffy is not a cat. Okay, so these two statements are logically equivalent. So you can try to phrase several statements like this, you can always turn any logical statement around and get its contrapositive, which is logically equivalent. So the contrapositive of this statement is that if the last column is not a pivot column, then the system of equations is consistent. And that's the same thing as proving that if the system is inconsistent, then the last column is a pivot column. Those two things are equivalent. So hopefully you'll get used to that after seeing several examples of this. Okay. Now, let's follow through on this argument. We want to show that if column n plus 1 of B is not a pivot column, then the system of equations is consistent. Okay. So if column n plus 1 of B is not a pivot column, then the leading one for row R is located somewhere in columns 1 through n. Then every preceding row's leading one is also located in columns 1 through n. Okay. So the last leading one is not in the last column. Since this is true, we can always construct a solution similarly to the examples that we've done above. For the pivot column, we can take the corresponding variable and actually, since we want to show the system of equations is consistent, we only need to show that there is one solution. So let me show you how this works above. Then he's making general statements here, but what he's basically saying is, suppose I want a particular solution for this system. Okay? One way to do that is to make all of the free variables equal to 0. Okay, so I'd make x2 equal to 0, and I'd make x5 equal to 0. Then my solution I can simply read off. x1 equals 6, x3 equals 1, x4 equals 9. And I also have x2 equals 0, x5 equals 0. So the point of this proof down here is that whenever the last column is not a pivot column, you can always do this. You can set all free variables equal to 0, and then the pivot variables or dependent variables are determined by the value in the last column. Okay, and that will always give you a solution to the system of equations. Okay, so that's really the idea behind the proof here. Okay. Okay, now this important point here is that now we know very easily and very clearly a characterization of systems that are inconsistent. You just reduce it to reduced row echelon form. You look at the last column and see if it's a pivot column. So as you say here, you could program a computer to do this. It's no longer art, it's become science. It's become an algorithm. And that's what we want to do. We want to reduce things to make them automatic. Because we don't want to have to do this ourselves. We want to be able to make a computer do this stuff for us. All right, so here the point is that if the last column is a pivot column, then n plus 1 is in D. But the last column cannot possibly correspond to a dependent variable because the last column is the constant column. It's not associated with any variable. Okay. All right. So now we have this characterization. We can explore the relationship between R and N for consistent systems. Now we've separated off the case where there's no solutions. We've seen before that it's possible to have a unique solution or to have infinitely many solutions. So now you want to see when you can tell there's one solution and when you can tell there's an infinitely many set of solutions. And that's what comes with this next theorem. Let's read this carefully. Suppose A is the augmented matrix of a consistent system. So we're saying already that the last column is not a pivot column. A consistent system of linear equations with n variables. So that means we know already it's going to have n plus 1 columns. Suppose also that B is a row equivalent matrix in reduced row echelon form. So this is the unique reduced row echelon form for A with R pivot columns. Okay, remember the pivot columns correspond to the dependent variables. All right. Then if R is less than or equal to n. Okay, we know that because the number of pivot columns is less than or equal to the total number of columns that correspond to variables. The last column cannot be a pivot column, so the number of pivot columns must be less than or equal to n. Now, if r is equal to n, then the system has a unique solution. And if r is less than n, the system has infinitely many solutions. Okay, so this characterizes the difference between systems that have infinitely many solutions and those that have a unique solution. If the number of pivot columns is equal to the number of total columns minus 1, then the system has a unique solution. And if r is smaller than that, then the system has infinitely many solutions. Okay, let's go through the proof. This proof contains 3 implications that we must establish. Okay, so what are the 3 implications? First of all, we need to show that if the matrix is consistent, then the number of pivot columns is less than or equal to n. That's the first implication. Second implication is this part, and the third implication is this part. Let's focus on the first implication here, that a consistent system must have less than or equal to n pivot columns. Okay. All right. Now, so let's see how this works out. Suppose, on the other hand, that the number of pivot columns is equal to n plus 1. Then every column of the reduced row echelon form is a pivot column, including the last one. But we know already that if the last column is a pivot column, then the system is inconsistent. So we've shown that in order to have a consistent system, it's not possible to have n plus 1 pivot columns. We've actually shown the contrapositive again. We've shown that if there are n plus 1 pivot columns, then the system is inconsistent. That's the same thing as showing that if the system is consistent, it cannot have n plus 1 pivot columns. In particular, it must have less than or equal to n pivot columns. Okay, let's go back to the second implication. Second implication, if r is equal to n, then the system has a unique solution. So let's see if we can show that. Okay, now when r equals n, we have n minus r equals 0 free variables because we've taken up all the columns with pivot columns. There are no columns left to be free columns. Okay, and then this gives us immediately the solution because we saw that when we have free variables, we have arbitrary perimeters. If there's no free variables, there's no arbitrary perimeters. The way you find the dependent variables is simply set them equal to the values in the last column. Okay. On the other hand, all right, so we've shown the second implication. All right, now we're finally getting to the third implication. If r is less than n, the system has infinitely many solutions. So if r is less than n, then we have free variables. And we've seen that we can choose any free variable to be any value you want. Once you have a free variable, there are infinitely many values that free variable can take. Each one of those values of the free variable will give rise to a different solution. So we have the complete theorem that the consistent system, in order to have a unique solution, it must have the same number of columns, the same number of pivot columns as it has columns. All the columns must be pivot columns. If you have a column that's not a pivot column, then you have infinitely many solutions. Okay, so that's it.